So the talk will be about the probabilistic construction of imaginary Liouville theory. Sorry. Put in my notes. Okay. Probabilistic. So I'm glad that there was Antti Kukanen's talk before, because it provided really a nice introduction to these topics. So in this talk, I will report joint work with Colin Guillermo, Rémi Rode, and Raoul Santachiara. And so it's based on work that we put on the archive. Link. So today's talk will be about imaginary Liouville theory. It is a family of conformal field theory with a central charge lower than 1. And I can already insist on the fact that the central charge is allowed to take any value less than 1. In this paper, we attempt to give a probabilistic definition of imaginary Liouville theory. And so I should begin by giving a brief introduction about Liouville field theory, what we usually understood to be Liouville field theory, and also to settle the notations for later. The probabilistic construction gives a meaning to the path integral approach to conformal field theories. Liouville theory is a that I denote like this. So Liouville field theory is a family of conformal field theories indexed by a parameter gamma, which is usually real. And the central charge of the theory is related to gamma by a simple equation. Okay, so you can check that this is greater than 25. And so it was introduced by Polyakov to study the fluctuation of the metric of Riemann surfaces. So in this talk, the Riemann surface will be fixed for simplicity. I will take the Riemann sphere with a metric which is conformal to the flat metric. Okay. It will be quite unimportant in the talk. And so in this picture, we are looking at observables that depend on the field, which is a free boson, a scalar field. Okay. The expectation values of the observables depend on the parameter gamma that I mentioned, and also on another constant, which is called the cosmological constant. So in the path integral formalism, it looks like this. So it's really the same thing as this talk. Okay, and this in general is a ill-defined mathematical object, and then the probability construction gives a mathematical meaning to this measure. So this is due to François David, Rémi Rode, Vincent Vargas, Antti Kukanen, Colin Guillermo. I did the probabilistic construction of Liouville theory. My notation are quite the same as Antti's, but I should write so similarly. The field phi is decomposed. It splits between a part which is independent of the point of the surface of the Riemann sphere, plus a part which is varying, which is called the Gaussian free field. The vertex operators are evaluated on points xj. and they are defined as the exponential of the field. Okay. So as we saw, it's under a regularization procedure, but I don't want to get into this. And then the averages I was mentioning, simply the product of vertex operators. So here we do an average over the zero mode. Okay. The setup will be quite the same for imaginary Liouville. This is a kind of the formulation of the path integral in the probabilistic language. Okay, so what I should mention here is that these kind of operators are, because of this renormalization procedure, defined only at a certain cost, that the charges should be lower than a certain value, which is called the background charge, and it's related to small gamma. Also, you can define this kind of correlation functions only if the sum of alpha j minus 2q is greater than 0. Okay. So these two conditions are called the cyber bounds. And so it was shown by the probabilistic approach that these are necessary conditions for the path integral to exist. Okay. So important achievement of the probabilistic construction has been the derivation of some exact results about the correlation functions of Liouville field theory. So Kupianen, Roden, and Vargas in 2017 derived the so-called Liouville formula, which is the formula for the three-point function of Liouville field theory. So it was a three-point function mentioned by Jörg Teschner in his talk. So I denoted by C Liouville. It depends on gamma, and it's a function of the charges of the vertex operators. So the form is a bit complicated. I won't put it entirely, but it's a function dependent simply on small gamma, and then you have a product over some special functions that depend on the charges. The arguments here are depending on the charges here. You have a product like this. And these are special functions related to bounds double gamma. So I think Shin-Sun mentioned it in his talk. And so, okay, so this is for Liouville C greater than 25. And as I said, I'm interested in C less than 1. So what you want to do basically is you need to do some rotation of the parameters in order to go to C less than 1. So as you can see from the expression of the central charge over there, gamma should be sent to imaginary values. So I do just a reparametrization of the quantities here. So beta is real. Okay, the charges of the vertex operator should also be rotated. Okay. Great. And the Q background charge is also, I change the parametrization. Okay, beta over 2 minus 2 over beta. So yes, so I want to go to C less than 1. The problem is that this function of Liouville is not defined when gamma goes to imaginary values. This is because of the special function you have here. So it is not defined precisely when gamma takes imaginary values. So in fact, in 2005, Samuel Chikov, a physicist, introduced cousin function of this DOZZ formula, which is called the imaginary DOZZ formula. And in fact, it was it is another solution of Stegner-Schiff's relations, and it was thought as a kind of non-physical solution, maybe to this Schiff's relations. So, imaginary DOZZ. Okay, depends on beta. So this is for C less than 1. Okay. But the story is that C less than 1 is precisely the range of validity of a lot of statistical models, such as percolation, Ising model, SLE, or CLE. And in fact, it was observed that starting from 2011, with Delfino-Vitti's conjecture, that certain observables, for instance, in percolation, could be described that this kind of formula. So this 3-point function is not contained in rational CFTs. It is not the 3-point function appearing in minimal models, and so by the time there was no CFT that would contain this 3-point function. So 2011, the Delfino-Vitti's conjecture is that in percolation, the probability that 3 points lie on the same cluster is precisely given by the imaginary DOZZ formula. In 2015, there was another appearance of the DOZZ formula with the Ikleff-Jacobsen-Saller conjecture about the nesting loop statistics in ON models. And both formulas were proven. So in 2021 by Hong, Kai, Sun, and Wu, in the case of CLE. Okay. So there was a renewal of interest for the imaginary DOZZ function. And the goal of this talk, in fact, will be to construct a CFT whose 3-point function is given by the imaginary DOZZ. Are there some questions now?
Excuse me. Is this inequality can be written by the conformal weight, or it's not related to conformal weight?
It's related to the convergence. You can see it. Yeah, it's kind of related to the conformal weight now, I think, because the conformal weight here would be alpha Q minus alpha. And I think, yeah, when alpha gets greater than Q, you will have a change of sign in the conformal weight, and then you have some divergence, basically. It indicates that the renormalization procedure won't work anymore, roughly.
Can I make a comment?
Yes.
Yeah, so my comment is that actually this conjecture IJS, this was proved in 2021 by Morris and me. But then this Delfino-Vitti was proved in 2024, actually, by this one.
Ah, okay.
So the current archive version is updated version.
Okay. Thank you. Yes.
You said up there that we need to rotate the central charts for a very good reason, of course, because we want central charts to be less than 1. But why do we want also to rotate the alphas? What is the reason behind that?
I mean, I can justify by statistical physics, like the vertex operators, the observable you're interested in will have imaginary charges. Yeah, but I don't know if it's a very satisfactory answer. Okay. So we saw that going to C less than 1, you could run into trouble at the level of the 3-point function. but it is also true at the level of the path integral. So I want to give you some intuition about the kind of problem we are running into when we are going to C less than 1. So let me rewrite. I just erased, of course. So for Liouville, with C greater than 25, I can rewrite, sorry, the expectation value by switching the expectation value over the Gaussian free field and the zero mode integration. So it's a elementary kind of elementary integral relation. I think it appeared in the paper Polyakov by Colin, Rémy, and Antti. So if I integrate over the zero mode,
this was already in the first paper of David.
Okay. Sorry. And you will see this form is quite G. Next. And this is elevated to the power to some power which is real. So here in the C greater than 25 setup, this random variable, depending on the Gaussian free field, will take positive values. So there is no problem in having even strictly greater than 0. There is no problem to have real powers over there. But then you do the rotation to a C less than 1, then this random variable would become I beta here. I should say this. And so you will have a complex valued random variable to a power which is real. And then you have you run into trouble because you have a choice of branch which you don't have under control. So yeah, so that's basically one of the problems that is happening at the level of the analytic continuation. Yeah. Okay, but maybe you can wonder. Okay, this is a problem in general. If I have generic values here, so this is a problem when it is real. But if the value here is an integer, basically there is no problem because there is no choice of phase to be made. Okay, so this is a kind of intuitive argument, a bit heuristic, but in fact it was put under, I mean, it was made rigorous by the model introduced in 2023 by Colin, Rémy, and Antti, which is called compactified imaginary Liouville. So I just give a brief statement about compactified imaginary Liouville theory. So the difference with the setup I am interested in is that the field here takes values in a quotient of the real line. So R quotiented by 2 pi R, and R is greater than 0. It's a compactification radius. Okay, and so in this setting, because of the compactification, in fact you have constraints on the vertex operator charges. Basically, you have alpha j's that satisfy those conditions. And so you end up with a conformal, with a central charge, which is rational. Okay. So this is related to what we want to do today, but not really because we have too much conditions. And as I said, I want to give you a theory that whose three-point function is imaginary DOZZ. And imaginary DOCC is defined for any values of or I mean, not only on with those conditions. Okay. So in that case of silt, you have indeed this exponent, which is equal to minus an integer. Okay. And this is called the neutrality condition. I think it rings maybe a bell for some of you. Neutrality condition. So in fact, the correlation functions of silt are given by so-called Coulomb-Gas integrals. Coulomb-Gas integrals. And so they are the same as the one arising in the minimal models. And so you have a rational central charge. Okay. So for us, we want to go beyond. We want to have a generic central charge, and we want to have charges that contain real values. Okay. So here, so without yes.
So if you take this condition, you exactly get the minimal model. So
it is still, I mean, the correlation functions are the same as the minimal models. The algebra has not been fully worked out yet, I think.
I feel of the minimal model of two indices. Two integers.
Yes, and I think this is related to the fact that in the probabilistic construction, you see that the potential has only one screening operator. There's not the second screening operator. So the second screening operator should appear at the level of the algebraic construction. I don't know if it's. So maybe you can discuss
it's
with
a subset of the minimum.
So you get to one sensor.
Yes, 3 minutes. Okay. So I want to tell you, yeah. So our idea to go beyond the neutrality condition. I mean, it is related to an idea of Witten in 2010. So the idea is that you should allow your field, so phi, to take complex values. So it's okay. Initially, it was taking real values, and now we are allowing it to take complex values. And so Witten produced an argument based on the theory of Fimbo. It's related to Morse theory. So okay, I don't want to last too much on this. And in fact, we jointly with physicist collaborator, so Shanyu Tsao, we investigated a bit more the proposal of Witten to do the analytic continuation. And we acknowledge the fact that, in fact, having the field take complex values was a bit difficult in the probability construction. So this was the starting point of our collaboration with Colin and Rémi. And in fact, we believe that we found a way to allow the field to take complex values, but in a way coherent with the probabilistic construction of Liouville. So I write the proposal for the path integral. So this is a proposal. So the vertex operators have imaginary charges. Okay. And so So you see, it's very similar to Liouville reduction. So the big difference is that the zero mode is allowed to take complex values. So in fact, it is as we allow the field phi to be C plus the Gaussian free field, and this is now complex. So C belongs to, in fact, to a contour in the complex plane. So I write it with the letter U. And why? Because the shape of the contour itself is quite like a U. So I write it like this. So the contour, like that. So it goes from 0 to 2 pi beta. And then you have also branches that go in the imaginary direction. So it's an oriented contour like this. Okay. All right, so this is a proposal for the path integral of imaginary Liouville, non-compact. An interesting feature of this is that, okay, I can rewrite the integral of the zero mode in this way. So, okay. I can split between the different branches. So branch one will be like this. Okay. And you can see that, in fact, it's really a trivial computation, that this one is proportional to that one. And the factor is just a phase, and it's related to the sum of charges. And what you see is that precisely when this number is a natural number, the two parts compensate, and you only have integration between 0 and 2 pi over beta. And so in that case, the integration control reduces to a finite interval. And in fact, it's exactly the case of the compactified imaginary Liouville theory. So, and recall that the correlation functions were given by Coulomb-Gas integrals, minimal models. Okay. So in fact, we have a theory whose correlation functions, when at charge neutrality, reduce to the Coulomb-Gas integrals. And the good thing is that it is exactly the behavior of the imaginary DOZZ formula. So, yeah. So imaginary DOZZ. Neutrality is exactly the Coulomb-Gas integrals with a certain number of screening. Okay. Great. So it seems that in our path integral, we have the same mechanism. Yes, 1 minute. Okay. So here I should give you a warning. The integral here, it is quite a complicated mathematical object because of, mainly because of one thing, is that we change the integration over the zero mode, that we should really worry if this integral is convergent. So yeah, probability, we often have convergence issues. So for instance, for the moment, it's only a conjecture. So conjecture one is that the integral is in fact convergent. So if I look at this function of the zero mode, which is related to to be interaction term. We believe that when we go on the branches of the U contour, that is when C goes to minus I infinity, this function has the following behavior. It is decreasing, and it has an algebraic decay with a power which is positive. Okay, so this is really a non-trivial statement, and it's a conjecture that we made based mainly on numerical analysis, but also on the exact analysis of a simpler model. So basically, when you replace the integration here of the whole complex plane by integrating only on the unit circle. So T. Okay. Okay, so I can talk about this later because we are. I should finish. Conjecture 2, and I end with this. Is that the 3-point function is in fact imaginary geodesy. And this we checked with a numerical analysis, and there is currently work also with Baptiste to prove that, in fact, to prove word identities, then BPZ equations, and maybe have at least a heuristic proof that the 3-point function of the theory is indeed imaginary geodesy. Okay, so thank you for your attention, and I put a last the results of the numerical simulations very quickly. Sorry, very quickly. Yeah. Okay.
I'm being a strict chairman because there is a conflict of interest, so don't want to abuse the.
Right. Yeah. So this is the kind of results you have by numerical simulations. You can find them in the article. So basically, numerical simulations would rely on using the Gaussian on a computer. Here I'm fixing alpha 1 and alpha 2 and just varying the third vertex operator. And you see that it matches, like the numerical simulation matches the geodesy formula with a relative deviation that is quite correct up to certain extremal cases that we can discuss. But okay, thank you for your attention.
So while Jan is preparing, we have just one quick question. Someone have a quick question?
Yes. Maybe I am confused. When looking at SLE from a CFT point of view, we are interested in operators which are not in the CATS table. 5.0 something, 5 are the correction function of those operators given by that.
So you are talking about the correlation function of operator in SLE,
which create any number of SLE lines in the back.
In fact, I don't know a lot about SLE so I not tell.
Yes, it should be the final theory.
Okay.
When if you the diagonal one,
SLE does.
Yes, we have we have
to the right of some point, any point. These are tested by operator of dimension 0.
Yes,
and this is what we call the zigzag.
Is probabilistic is a complicated question actually. Like to find these 0 operators which are not real. Many times they go out the probabilistic when this integral does not converge. So for this kind of value. So I think let's thank Roman again.